We've already seen that architectures use the stack to transmit some information between callers and callees. And we know that the y86 uses the stack to store, for example, the return address after a call instruction, as do most architectures. In order to use the stack effectively, we structure the stack into collections of data called stack frames. And that's what we're going to talk about here, which is what exactly is a stack frame and how does it get created. So as I said, the call instruction already puts the return address on the stack, but we also use the stack to transmit local parameters to transmit parameters if they are too big to go in registers or if we have too many. And we also use the stack to store local variables. Since in a recursive procedure, you might have many, many instances of a function and each one needs its own local variables. So the structure that we're going to use on the stack to organize this information is called a stack frame. So let's look at a picture. What I'm showing here are two stack frames. Now remember, our stack grows from high ordered addresses to low ordered addresses. So from max address down to 0. And when I draw them, I'm going to draw them starting on the right and growing to the left. So here, the rightmost stack frame over here is in fact a caller. You might think of it as main, right? So here is the first stack frame. When this function invokes another function, it creates another stack frame. And if that function were to invoke another one, it would keep growing. So the stack is going to keep growing to the left. And each procedure that we call is going to construct a stack frame. Now, it turns out that there are two different ways you can manage your stack, and I'm going to step through both of those. The first technique assumes that you don't have a base pointer or a frame pointer. We don't have a reserved register that we're going to use to keep track of our frames. And so instead, we'll use the stack pointer to do that. So let's imagine that we were executing in a function and we just made a function call. So we know that that function call pushed the return address onto the stack. So our stack pointer is pointing at that return address. The first thing we're going to do to construct a stack frame is we're going to allocate space for local variables. So what that looks like is we compute how much size we need for local variables. This is information that the compiler has. So it's the compiler that is figuring all this out and is generating the instructions in the compiled code that do the following. So the first thing we do is we figure out how much local space we need. In this case, we need 32 bytes. And then what we're going to do is we're going to decrement the stack pointer by those 32 bytes to leave space for those local variables. So using the color scheme now, we have the return address, just like we had before. And then we also have some space for the local variables. And then we're going to call this whole chunk a stack frame. So once I've set up this stack frame, if the function wants to access either its local variables or the parameters that the caller passed on the stack, those would be the parameters here, those are both going to be positive offsets from the stack pointer, right? Lower addresses are down here. The stack pointer is at the end of the stack frame. And so both these variables and these variables will be reached by adding some positive value to the stack pointer. And because the compiler has constructed this frame, the compiler knows exactly what those values are. So at the beginning of a function, what you'll see is that the compiler has generated these instructions that subtract something from the stack pointer and set up this stack frame. Similarly, at the end of a function, you'll see code, which we call the postamble, which will tear down the stack frame. So when we built the stack frame, we decremented RSP. To tear down the stack frame, we're going to have to add that value back onto RSP. So conceptually, we've kind of removed things from the stack frame, but you and I both know that in reality, whatever data was on the stack, it's still there. We're just sort of ignoring it. And then after I've torn down the stack frame, I can do a return, and that will move the stack pointer back to where it was before the function was invoked. Now there's one more thing that the caller has to do. Remember what the caller did to make the call is it loaded some values in registers, and it also pushed some things on the stack. Once the function returns, it no longer needs those values on the stack. So in the caller, we're going to move the stack pointer again to sort of pop those values off the stack. I don't need to read them into a register. I just need to restore the stack pointer as if those values weren't pushed on the stack. So that's how we do stack frame setup in a function preamble and then tear down in a function postamble when we don't have a base pointer. Now let's look at what this base pointer is. So in this case, I designate a register on the y86, it's RBP for base pointer. And I designate that register to basically be the register that keeps track of the current stack frame. So before I've invoked another function, RBP points to sort of the beginning of my stack frame. It doesn't point to the very beginning because we know that call has put a return address there, but the very first thing that a preamble is going to do is to store RBP there. Okay, so that's going to be the old value of RBP, and then the RBP register itself points to the beginning of the stack frame. Okay, so now let's say I want to make a function call. Well, we know what happens. We push an address, the return address. That's just like before. But now the very first thing that the preamble code is going to do is it's going to save the base pointer. So it's going to push the base pointer onto the stack using a regular old push queue instruction. What that does essentially is create a linked list between these stack frames. So it used to be that our stack frame was here, and instead our stack frame is now going to be here, and we're in the process of building it. So we've taken the contents that were in RBP, we've moved them into the space, and then we've taken RSP and we moved it from where it was one more location because we've pushed something. Okay. Next, we're going to, now that we've saved RBP, we can now move RBP. So what we'll do is we will change the value stored in RBP to be this new location of the saved frame pointer. So we just do a register to register move from where the stack is pointing into the base pointer. And so now we're in the process of creating a stack frame here. And just like when we started, RBP is going to be pointing to the beginning of the frame minus that return address. Then, just like before, we're gonna subtract some space off for our local variables. And now we've established a stack frame. So we've done essentially the same thing. We've just added one more step where we save the base pointer. Why did we go through all that work? Well, now, instead of accessing locals and variables from the stack pointer, we can access everything off the base pointer. And you have this nice division where local variables are negative offsets from the base pointer. And if there were stack parameters in the caller, those would be positive offsets from the base pointer. So now the stack pointer can go do whatever it wants. You can push some values if you want to save them, you can restore them, whatever. And the base pointer is unchanged. And so it's easy to know exactly where your local variables are and any of your stack parameters. Just like in the no base pointer case, when the function wants to return, we have to tear down the stack frame. And so we're going to reverse everything we just did. What does that look like? Well, first, we're going to move the stack pointer back to where it was. So we add that value back into RSP. Now we're going to restore the base pointer. So we pop that. And now we're basically in a state where we're ready to return to the caller. And so now we're right back where we were, where we started. So these are the two different ways that you can implement calling conventions between callers and callees and make sure that your compiler generates code that lets you access all the variables that you need to access.